Okay, this is lecture number 6 of the series of the digital image processing. Today, I would like to talk about uh, today. Let's see. Okay, today I would like to talk about digital image processing, lecture number 6. This is lecture number 6 of the series of digital image processing lecture. And today the area is about uh, indexing. Okay, today it's about the um, pixels, different pixels on the image, the relation of the pixels, the relation of the pixel. Let me see again. The relation of the relation different relation of the pixels on the image, digital image. So basic relation between the pixels of the image. Okay, research. And for instance, we have the conventional indexing method is like this. We have two coordinate, two-dimensional coordinate, and this is X and Y. And for each picture element, we assign the coordinate, for instance, from left to right, X minus 1, Y minus 1, and X and y minus 1 and x plus 1, y minus 1. Because this is x minus 1, here is x minus 1, here is here is x plus 1, and here is y minus 1, here is y, here is y plus 1. This is so on. You can, for instance, the main point, main pixel is x, the neighbor of the pixel x coordinate x and y. So these are all neighbors here. So I will define later. Okay. Uh, a neighborhood relation is used to tell the adjacent pixels. Uh, it's useful for analyzing of the region drawing and so on. For instance, we can define the neighborhood of the pixel P. This is pixel P with the coordinate XX, but we define the four neighbors. Four neighbors contains this one. Again, yes, I have to, for instance, this is X, Y minus 1, X plus 1, Y, X, Y plus 1, X minus 1, y. This is y, here is x minus 1, this is x, this is x plus 1, this is y minus 1, y plus 1. So these four pixels are neighbor of the P. We call it four neighbors. So we write it N4P. Four neighbors relation consider only vertical and horizontal neighbors. So if, for instance, P included in N4P, this implies that P also included in N4Q. For instance, this is Q. For instance, you have a Q here, a pixel This is pixel P, this is pixel Q, or this is pixel Q, for instance, not here, for instance, here. So if Q included this set of the four neighbor, then if main point is here, Q, then also P is included to the N4Q. So this is the both side relation. Next, eight neighbor. Okay, this is four neighbor and this is eight neighbor. Eight neighbor consider all surrounded of pixel P. I cannot. I mean, each one. I don't want to say the name of each one. You know, x minus one, y minus one, 2x plus one, y minus one, and we call it N8P. Okay, eight neighborhood relation considers all neighbors pixel, all neighbor pixel. Also, we can define diagonal neighborhood of the X. This neighborhood and this pixel relation is very important when we consider the analysis on the digital image for different growing, segmentation, and compression, all kind of the uh, machine vision and artificial intelligence. You can use this kind of. The diagonal neighbors of the P is this four. We have four diagonal. This is diagonal. Diagonal. We have two diagonals. So four member. We have x minus one, y minus one to x plus one, y plus one. So because it's diagonal, we call it NDP. Diagonal neighborhood relation considers only diagonal neighbor pixel. So if Q is here and Q is included in the diagonal number of the P, then we can say that P also included of the NQ, N and DQ. If Q belongs to NDP, then P is also include to NDQ. Maybe this is also both sides. Okay. Also, we can here define connectivity is adapted from the neighborhood relationship. Two pixels are connected if they are in the same class. For instance, this color, same range of intensity, and they are neighbor of each other. For instance, for P and Q from the same class, for connectivity, for instance, P and Q are four connected. If Q included or belongs to N4P, for instance, pixel Q belongs to relation, N4 neighbor N4P, or eight connectivity is P, Q are eight connected, then we say that if Q belongs to N8P, then there are eight connected. Mixed connectivity, connectivity is, for instance, P and Q are M connectivity if Q belongs to N4P, or for instance, Q is N4P, and also this is also mixed. For instance, if N4P, we have N4P intersection with N4Q is empty. Let me see this N4P and N4Q. For instance, here N4P, these two, N4P is this one, and N4Q for this. If this is Q, then N4Q is different from maybe you can assign Q is different, so you can say that this is different. And then if it is no element inside, For instance, P is the N4. Okay. Once again, if P is Q, if Q is included in 4PQ and also 4 included in NDPQ, it's like this, that if P is 4 and Q is D, so maybe something like this. For instance, the neighbor of the N4, we have this set of the element, but neighbor of the A and D, these are this element. Cross, I mean, the intersection of these two are empty. Maybe it's better to write it in different way here. Okay. Also, we have different relation here, transitive closure, and so on. Here. Relation equivalence and transitive closure. A binary relation R on the set is set pair of the element from A. For instance, we have two element, two pixel. If A pairs A and B, these two pixel. In R notation, often is called ARB, which means that the pixel A is related to pixel B by some relation. For instance, we have 4 pixel here, P1, P2, P3, P4. These P1 to P2, P3 are, let's see here, I will come back very soon. For instance, for instance, the P1, P2, P3 are neighbor, for instance, N4 neighbor, but P4, but P4 is not related to any other three under the relation for connected or something like that. Okay, let me return to my point here. And we have relations, a binary, we define the different relation. A binary relation R over a set of A is said to be reflexive. For instance, we have 2 pixels. A in a set of the A. A is the set, A large A is the set of the pixel. A is reflexive to a small a, is reflexive to itself, A. So we write it pixel A is reflected to itself, A or A is related. Or symmetric, if the pixel A and B are really in a set of the pixel, for instance, you have in image, a set of image, for instance, you are in the regioning or segmentation of the region A, you have different pixel, and A and B are related with this, A and B. It implies that B or A, also B is related to it. So if A related to B, then B related to A. This is symmetric. Symmetric is for each pixel that which AB. If AB implies that B or B implies B or A. Transitive, another relation is another, I mean, the specification of the relation is that if A and B and C in the set of the region, for instance, region of the picture, in A, then A related to B and B related to C by some relation, for instance, neighbor or whatever you define, implies implies that A related to C. So if A related to B and B related to C, if we have A related to C, this is, we call it transitive. So we have reflective, reflexive, symmetric, and transitive. A relation satisfies in a region of the digital image between the pixel. A relation satisfies these three: reflexive, symmetric, transitive. Not all of them, but all, or not all pixels like this, but for instance, a region is in a set, there are three. A relation satisfies these three properties is called the equivalence relation. So what is equivalence relation? Equivalence relation is a relation in a region of the digital image between pixels that is reflexive, symmetric, and transitive. If it is not, then we can make it. How? For instance, we can make a matrix or binary matrix. For instance, if A and is related to A1. So there is the two pixel A and A are inside the relation A. Also AB. So here is just one. But if there is no relation between A and C, so there is no AC here. And also BD, with B and B and D. For instance, here, okay, I still have to change this. If B is related to D, then you have one here, but the other place is zero. So we make this kind of the binary matrix if they're related, these pixels are related. So with that relation. C is E. C is related to E, so one is here. D related to B is here for this relation in this set of the relation. But there are no. If you want to have all relation, for instance, you want to have transitive and so on, so in this case, you have to do this kind of thing. If, for instance, A related to B, we will return A to B and B to D. But should be A to D, but there is no transitive. So if you want to make this kind of relation like this, A, B, and B, D, then we have AD. If you want to have AD here, you with the matrix B here, B matrix, we call it B matrix with the relation R. We make the matrix B plus with this calculation. B plus B multiplied by B plus B multiplied by U with n dimension. If your matrix is n dimensional, the region is n dimensional, n by n, so it is like this. But please understand that this plus is the OR, is the logic OR gate, and multiplication is AND gate. That's why. Because it is 0, 1 only. So if there is relation, there is 1. If there is no relation, there is 0. If some point are missing here, for instance, here, some point is missing. If you compare with these two, here is missing, here is missing. Sorry. Here is missing, so also, oh, here this point B and B is missing, but the next one is here. So if you want to make this B plus or R plus set, which is the B plus matrix, you should follow this kind of the calculation, and this is up to you to make this kind of the relation. Okay. Another subject here is the adjacent pixel. A pixel P is adjacent to pixel Q if they are connected. For instance, two image sets. One is here S1, one image is here S2. Are adjacent if some pixels in S is adjacent to some pixel in S2, in S1 and S2. For instance, these two pixels of S1 and S2 are for included for neighbor or so on, whatever. There is some relation. We can define type of the adjacent, 4 adjacent, 8 adjacent, or M adjacency, and depending on the type of the connectivity. Okay. And a pass also, you can take a pass. For instance, in robotics also, you need to define some pass. A pass from the pixel P with the coordinate XY, go to point Q with coordinate ST. Then it should go to X0, Y0 to Xn, Yn. And it's like this from X0, Y0 to ST, which is Xn, Yn. So you have to go this side, for instance, then go this side, and this side, this. This is, for instance, a robot want to use a pass from P, go to Q. We can define type of the pass, 4 pass, 8 pass, or M pass, depending on the type of the adjacency, adjacency. Sorry. For pixel P, Q, Z, this is a different. This is a again. Here, for instance, this is the this is distance, just distance, but it missed here. Okay, go to distance. That we define distance. Distance is kind of relation. Again, I will use this for you. Point. For example, pixel P and Q and P, Q, and Z with the coordinate X, Y, S, T, and U, V with D. D is the distance. Is the distance function or metric for between the distance between P and Q and Z. For instance, we have different pixel with this kind of coordinate. Then we define the distance function D or metric. What is the definition of the relation? We call it distance relation or distance function. Distance relation should be between P and Q should be more than or equal 0. If P or equal P is Q, then is 0. This is first condition. The second condition should be reverse also. If PQ, then QP also. As I said, A R P, then B R Q. So it is reflective. So that's why if we have the relation D is between P and Q, then relation is DQP. And also, because we assume 3 pixels on digital image, for instance, the distance between P and Z always less than or equal the summation between distance between PQ plus distance QZ. It's like the triangle. You have a triangle and then you go straight P to Z or go to P to Q and Q to Z. Always should be, this is a straight line is less than or at last equal if point Z is over the line PQ. For instance, we have different kind of the distance. One is the example is the Euclidean distance. The Euclidean distance is not only distance. As everybody know, Euclidean distance is x minus s square plus y minus t squared and root of this. This is Euclidean distance. we define another distance. For instance, 4 distance, we call it city block distance. This is city block distance, which is x minus s, absolute value plus y minus t. So the point between here and here has 2x, and s is between pixel X and pixel, for instance, pixel P and pixel Q here. So difference of the X is here 2, and plus difference of the Y, which here is 0. So the summation of this absolute value, so it doesn't matter minus. So this is 2, this is 2, also this is 2, because the absolute value of this and this is 1 plus 1, so it is 2. 1 in vertical, 1 in horizontal, so it is 2. And here is only vertical is 2, and so on. So the geometric place of the 2 is this shape here, like diamond, and with the distance of 1 is this small one. So we call it D4PQ. Pixel D4PQ is 1, is 4 neighbor of course, P. Another is the 8 distance. This is, we call it chessboard distance, is defined as maximum between x minus s, y minus s. So we define x minus s or y minus. Here, x minus s is larger, so take the maximum. So this one. You can define for yourself the minimum. I cannot write here, but you can call it, you reach to different shape on the image. Here is this is for D8PQ, which is maximum between x minus s and y minus t, vertical and horizontal absolute value, which is maximum or which is minimum, is different shape. For instance, this is the location of the 2 distance, then this is the location of 1 distance. So in this case, you can separate the image or portion of the image which is related to your algorithm. You want to do something, this kind of relation can be very helpful. Pixel of the with D8P, 1 is 8 neighborhood. This is 8 neighborhood. Okay. From here, I think this is getting larger, 30 minutes. And next, the one I would, in the next one, I think the algorithm, logical operation, arithmetic. I mean, arithmetic includes logical operation. For instance, we have addition of 2 pixel P plus Q. This arithmetic operation is over the brightness. For instance, you have the gray level digital image with 2 pixel P and Q. Then you add these two, or you subtract, or you multiply, and so on. Or you make a logical arithmetic operation. For instance, P and Q and P and Q or not Q, which is complement of this. This kind of the relation and more image geometry I will discuss in next lecture, which is number 7. But here I finish lecture number 6 here, and thank you very much. I stop here.